Hi everybody, this is the recitation video for chromatography, experiment 6, parts A, B, and C. This is the experiment that we will do next week in lab on the 19th. So just a couple of reminders, the OChem lab is open from 8:30 to 3:30 Monday through Friday for melting point and weight. We won't have lab or recitation on Thanksgiving week. And remember that when you're registering for classes, the organic lecture and lab are co-requisites, so you have to register for both. Okay, so questions answered by thin layer chromatography. We can answer, are these two compounds the same? If we have two different compounds, we can use TLC to answer that question. We can use it to answer the question, what is the minimum number of compounds in this mixture? We can answer the question, is this compound pure? Is the reaction finished yet? Is this a good solvent system to use for large-scale purification? And so essentially what TLC allows us to do is to check the number of components in a system, the number of different compounds. We can count them because they all have different properties, and we can separate them using thin layer chromatography and then count them. So chromatography works by separating a mixture by distribution between a stationary phase and a mobile phase. We call this solid-liquid partitioning. So this is very similar to the kind of behavior that a compound has in a separatory funnel. Remember that in a separatory funnel, we have a compound that spends some time in the aqueous phase and some time in the organic phase, and it can kind of move back and forth depending on its polarity and which phase it's most stable in. That's the same idea here. We have two phases, a solid phase and a mobile phase, and the compound is going to spend more time on one or the other, similar to the partition coefficient. It either likes the stationary phase more or it likes the mobile phase more, so it spends more time in that phase. So we're doing solid-liquid chromatography, where the solid is stationary, that's the plate, it's a solid, and the liquid is mobile. So we'll use capillary action and dissolve our compound in a solvent and use the plate to separate that liquid. So this is the idea. The solid is the plate. It's literally, it looks like an index card, and the index card has some material on it, and we spot our solution containing our compound of interest or our mixture of interest onto the plate, and then we can put the plate in the into the developing chamber, and the compound will then start moving between the solid phase and the solution phase, and it kind of moves back and forth and establishes an equilibrium. So the compounds are always moving back and forth between the two phases in an equilibrium solution. The stationary phase consists of a fine powder that's been pressed to the back of the plate. This creates a large surface area for good separation. So the solid powder is coated onto a support backing to make a plate. So we have this powder, and then it's pressed hard and adhered to the back. It kind of looks like aluminum foil, the backing of the plate. So the backing can be plastic, aluminum, or glass. What we do is we take our plate and we make a solution with our mixture or our compound of interest, and we take a capillary that kind of looks like a melting point capillary, just a really thin glass tube. We draw a little bit of solution into our thin glass tube, and then we make a very tiny spot onto our plate by pushing the solution onto the plate until it makes a little spot. And then once the solvent dries, once the solvent evaporates, what's left on the plate in that spot is your mixture of however many compounds there are. So the mixture is applied as a spot near the bottom of the plate. We want to make sure the spot is very small as possible. That's why we use this teeny tiny melting point capillary. So after we have our plate and we make our solution and we put a spot on the bottom of our plate, then we're going to make an eluting chamber. And so this chamber, you can see it's kind of a glass jar. The glass jar has a small amount of solvent on the bottom, and coating the sides of the jar is a piece of filter paper that's pushed down far enough so that the solvent will be pulled up the filter paper. The idea is you have this filter paper kind of on the inside of the jar that's soaked in solvent, and it gives the solvent more surface area to evaporate, because we want the chamber to be filled with the fumes of the solvent, so that there's a large amount of gas phase in the chamber. That's also why we cover the chamber. We cover it because we want there to be a high concentration of gas from our solvent inside the chamber. So the bottom edge is placed in a liquid, a shallow pool of liquid. It can't go over the spot. The spot must be above the solvent. The liquid rises through the solid powder via capillary action. So just like if you dip a paper towel in some water, the water kind of climbs up the towel. That's what's happening here too. The solvent climbs up the card by capillary force. The moving liquid carries the components up the plate at different rates. So depending on how many compounds there are in our sample, some of the compounds are going to adhere to the solid phase more tightly, and some will spend more time in the mobile phase. So as the compound kind of moves back and forth from the mobile phase to the stationary phase, it's slowly moving up the plate. The rate at which the compound moves up the plate is a function of how much time it spends in each phase. Compounds that spend more time in the mobile phase, in the liquid, will go faster because they're traveling at the same rate that the liquid is up the plate. Compounds that spend more time adhered to the solid will move slower because they're stuck on the solid while the liquid goes by them. And so the different compounds spread out along the plate as a function of their different rates of travel, which is a function of their polarity, because that's going to determine whether the compound spends more time in the mobile phase or in the solid phase. So you only handle TLC plates by their edges. And this should make sense because we can absorb organic compounds onto the plate pretty easily, and if you have any compounds on your fingers or on your gloves and you touch the plate, then you're going to contaminate it with other compounds. So we only grab it by the edge. Lightly draw a pencil line 1 centimeter up from the bottom of the plate and mark where you will apply each sample. So the idea is we need to spot the different compounds on the plate, but we want to kind of have a guide to show us where to spot them. So we draw a pencil line 1 centimeter up from the bottom, and then we know we can put our compounds on that line. They all need to have the same starting place so that we can compare how far they traveled. If we start them at different places, then we can't directly compare them. So they all start on the starting line. Space each sample evenly. Do not scrape off the solid absorbent, so you have to use a pencil very lightly, because if you go too hard, it'll scrape off all the solid. Don't use a pen, because the pen will travel with the solvent, but a pencil won't. And pre-draw your solvent front line. Lightly draw a pencil 1 centimeter down from the top of the plate so we know how far the solvent is supposed to move before we stop the experiment. So you should practice spotting the plate before you do it on your big plate. TLC plates aren't cheap, so it's very easy to ruin them. So before we actually do the real deal on our real plates, we should use little scraps of TLC plate to practice, to make sure that we're making our spot as small as possible. So the tinier the spot, the better the resolution that we'll get. They'll be able to separate the components easier if the spot is smaller. And so we'll draw up the solution into a TLC spotter, briefly touch the spotter to the plate to make a small spot. Don't scrape off the solid absorbent. Don't make a spot larger than 2 millimeters. And check the spot size by visualizing under a UV lamp. And so we'll practice. It's a good idea to practice with the UV lamp so you can see how big the spot is as you're making it. Because of course, the spot, once we spot our plates, it's almost invisible. You can't even really see what you did. So the UV light will help, the plate will fluoresce, And so we can see the spots that we make if we illuminate the plate with a UV light before we spot. Use a beaker covered with saran wrap or a jar with a cap. We don't want the liquid to evaporate. Line the container with one piece of filter paper. It keeps the air saturated with solvent vapor so it doesn't evaporate off the plate. So this was that piece of solvent filter paper that we saw earlier that was in the plate. Soak a piece of filter paper with solvent. Add enough solvent to the jar so that the height is about 5 millimeters from the bottom, but not so deep that you submerge your spots. Remember, after we spot our plate, we need the spots to be above the surface of the liquid inside the developing chamber, so it can't be very deep. Add the plate, cover the beaker, jar, and watch it. You have to cover it because we have to keep the concentration of fumes high in the gas phase inside the chamber. When the solvent reaches your pre-marked solvent front line, remove the plate. So again, here's the setup. We spot our plate, we put it into the chamber. The chamber has a small pool at the bottom, but not too much to cover the plate. We have to have this piece of filter paper in there that's soaked by the solvent because it increases the surface area. And lastly, you have to cover the system so we keep all the gases in there. And then you'll watch the surface of the liquid. You'll watch the solvent front. That's the line where the liquid is. And when that solvent front reaches the line at the top of the card that you drew, then you remove and you're done developing. So be sure to let the plate dry completely before continuing. This takes a few minutes. So if you don't let the plate dry before you visualize it, then you'll be visualizing the solvent, which makes your analysis very difficult. Many compounds fluoresce under UV light, making visible spots. So this is what I was saying before, that some compounds fluoresce and they'll actually, you'll see a color, like you might see fluorescent color, it'll be blue. The plate itself, if we illuminate the plate without anything on it, just the clean plate, it fluoresces bright green. So most of the compounds that we're going to be looking at, they absorb ultraviolet light. And so the plate is totally green except for where the organic compound is, because the organic compound is going to absorb the ultraviolet light. So you'll see a black spot where you put your compound. So after we're finished developing our plate and we look at it under the UV light, we see where the spots are with the UV, and then we circle them with a pencil, because once you take the UV away, they'll become invisible again. So we want to be able to see them when we're done. Sometimes it's still difficult to see the spots even with UV light. And so what we can do as an alternative method of visualizing the spots, we can use iodine. And if we place the plate into a chamber containing some iodine crystals sublime very easily to create iodine gas. And if we put the plate into a chamber containing iodine gas, the iodine will bond with the most organic compounds and make a colored spot. So we can take those invisible spots, put it into a chamber with iodine gas, and the spots will become visible. So we can either use ultraviolet light to look for the black dots, or we can put the plate into an iodine chamber and look for the brown dots. So the partition, remember this is like the partition coefficient, the time that each compound spends in each phase, whether it be aqueous or organic when we're talking about extraction. We can apply that same kind of idea to chromatography, except the compound, rather than moving between two different liquids, the compound is moving between one liquid and one solid. So this is what we might see. On the left, we spot our plate, and we put that spot about 1 centimeter or so above the bottom of the plate, and then we make another line about 1 centimeter from the top of the plate. We call that the solvent front line. We're going to put our spot on the first line that we make, and then that's the original plate, and then you'll put the original plate in the developing chamber and watch it until the solvent front reaches the predetermined line, and then we'll take the plate out, visualize the spots, and after we visualize the spots, they might look something like this. And so what this shows us is that our original sample, we took an unknown solid, We dissolved it in some solvent and made a solution, but we didn't know how many compounds there were. We spotted it on the TLC plate, put it in the developing chamber, and then we see these 2 spots. So that tells me that I have at least 2 different compounds in my mixture. There might be more than 2 though, because there might be a 3rd compound that's hidden underneath one of those spots, which is to say that there might be 2 compounds that have very similar properties and travel at a very similar rate, so it might be hard to separate them. But what we can say for sure is that spot 1 and spot 2 are not the same compound. They're definitely different compounds. So there's at least 2 different compounds in this solution. Then we calculate what's called the RF, which is the retention factor. And the RF is easy to calculate. We start a line at the very bottom where we put our spots, and then we draw a line at the very top where we put our solvent front. And so the distance between the line where we spotted and our solvent front is 65 millimeters. And then we also measure the difference between where we started and where the spot is. So we'll have the total difference between the beginning line and the solvent front, and then the distance between the beginning line and 1, and then the distance between the beginning line and compound 2. And if you divide the distance that the spot traveled over the distance the solvent traveled, that gives you the retention factor. So it will always be a number between 0 and 1. If your spot is on the solvent front, then your RF value is 1. If your spot is on the beginning line and it didn't move at all, then your RF value is 0. So RF values are not exactly reproducible, which means that we can't look at an RF value in a book and expect to get the same RF value if we were to do the same compound in the same solvent. So what that means is that RF values are not absolute, they're relative. So if we spot 2 compounds on the same plate, then we can directly compare their RFs. But if we spot the same compound on 2 different plates, then we can't directly compare their RFs. So when we're trying to compare 2 different spots, we always spot them on the same plate, because 2 plates, we can't compare the details between 2 plates. And we should always spot the spots on the same line. So there's 2 different kinds of solid phases that are typically used in chromatography. We have silica gel, that's what's on the TLC plates, and that is the less polar option. And there is also alumina, and that's usually what's found in chromatography columns, and that is the more polar option. So initially all compounds are adsorbed to the solid phase. The solid phase is very polar, so polar compounds will move the, what do you think, slowest or fastest? Remember, like dissolves like, or things that have similar polarity like to interact. So if the solid phase is very polar, polar compounds are going to stick to it. If polar compounds stick to it, then they're not going to move very fast because they're stuck. They're stuck on the solid. They can't get into the liquid. Nonpolar compounds are more soluble in nonpolar phases. So nonpolar compounds move, what do you think? They'll move faster than polar compounds because usually it's a tug of war between polar and not polar. Just like with extraction, we have nonpolar organic and we have polar aqueous. The compound wants to go in one phase or the other. Here we have nonpolar organic solvent and polar silica gel. So it's the same thing. If we have polar compounds, they're going to be stuck to the silica gel and they won't move very far. And if we have nonpolar compounds, they're going to be stuck in the liquid and they're going to move really fast. Polar solvents are adsorbed on the solid phase, displacing all compounds. Polar solvents will move all compounds faster, polar and nonpolar. Small compounds move faster than large compounds. So the point here is that it's this tug of war between polar and nonpolar. And so your compound has to choose which phase it likes more, polar or nonpolar, and that's what does the separating. If both phases are very polar, then there is no separation that can occur because all of the compounds are going to have the same properties or the same behavior in the polar solid or on the polar liquid. They're both polar. They're both doing the same thing. And so we need to have our solvent be as non-polar as possible in order to get the best separation. Now, having said that, sometimes our compounds are so polar that if we use a really non-polar solvent, it can't even move it off of the line. So we need to kind of test our solvents and try to find a solvent that's polar enough to make the compounds move, but not so polar that it pushes everything to the top. So if the solvent is too polar, all the compounds may move with the solvent and not separate. If the compound is too nonpolar, all of the compounds will sit at the bottom and will not separate. Intermediate polarity can be obtained by using a mixture of solvents. The best solvent is determined by trial and error. And so generally we'll have a nonpolar solvent and a polar solvent, and we can mix them in different proportions to get solvent mixtures of different polarity, so we can optimize the polarity. So here are 3 plates. What we can say about the first plate is that it looks like it was not a very polar solvent. So remember, the compounds they're all going to stick to the silica initially. If we want to pull them off of the silica, we need to use a solvent that is polar enough that it will pull them into the solvent phase for a little bit before they stick to the solid again, and vice versa. So plate A, we can see that had the least polar solvent. In plate B, we can see that there they used the most polar solvent. Everything traveled to the top. And in C, we can see that they used an intermediate polarity, and you can see that they have the biggest separation between spots is on plate C. And that's what we want. We want the biggest separation between spots. If the spots are really close together, it's hard to tell them apart. And it's also hard to separate them, which is something that we use the results from this TLC experiment to help us actually separate these compounds. Right now we're just looking at the mixture. We technically separated it with those 2 little spots, but in those 2 little spots is probably 1 milligram of material, and we probably started with 1 gram, right? So this is not a way that we can actually separate all of compound A from compound B. This is just a way that we can look at it, and we can find the solvent that is the best, and then we can set up a different experiment to use that solvent to actually separate these. Okay, so that's the theory, that's the idea of TLC. Now let's look at the experiments we're going to do. We're going to do 3 experiments, 6A, 6B, and 6C. In 6A, we're going to use thin layer chromatography to identify the components of an unknown mixture. In part B, we're going to determine the best solvent for the TLC separation. Like we just said, we got to find the ideal polarity. And in part C, we're going to use TLC to monitor the time of a reaction to help us determine when it's complete. So in 6A, we will use TLC to separate fluorine, fluorinol, and fluorinone. You can see that these 3 compounds probably have different polarity. Think to yourself about which one is most polar and which one is least polar, and where you might expect to find those on a silica plate if we ran the experiment with the right solvent. So we'll dissolve 1 milligram of each solid in a few drops of acetone or dichloromethane to make each sample. Your white-capped vials or small test tubes work great for this. Practice spotting first on the designated practice plates. Use different spotters for different compounds so you don't contaminate your plate by using an old spotter. Then spot the following, all on the same line: pure fluorine, pure fluorinol, pure fluorinone, and your unknown, which is already dissolved in acetone. May contain up to 3 of the above compounds. So that means that you may have only fluorine, only fluorinol, or only fluorinone in your unknown, or you could have 2, fluorine and fluorinol, or fluorinol and fluorinone, or you could even have all 3. You might have all 3 in your unknown. Your job is to spot these 3 pure samples so we have a reference to compare it to, and then spot our mixture, our potential mixture, and try to match up the spots and see which compounds are in our mixture. We'll develop the plate with methylene chloride, dichloromethane, then visualize with ultraviolet light and circle the spots with a pencil, and then we can visualize with iodine. And the iodine can sometimes help us see spots that we couldn't see with the UV, or it sometimes helps us see those spots better. So that's why we're going to do both. Okay, so make 3 identical plates. Spot your given mixture. This is for 6B. Spot your given mixture and the 2 compounds which it contains. Prepare samples the same as before. Develop each using the 3 solvent systems listed on the bottom of page 48, and then visualize with UV light. So again, we have a mixture, but we don't know the best solvent to use. In our last experiment, it said use methylene chloride. Well, we don't know which one we're supposed to use. So the way that we figure out which solvent is best for this separation is by making the same exact plate 3 times and then running each of those plates in a different solvent system and seeing which one gives us the best separation, like that previous slide where we showed those 3 different plates. And then finally, in experiment 6C, we're going to monitor a chemical reaction, the reduction of a ketone. So we're going to start with fluorinone and use sodium borohydride, which is going to reduce the fluorinone to fluorinol. So we're going to be doing a chemical reaction. TLC can help us determine when our chemical reaction is done. Sometimes we don't know when it's done. Do we react it for a minute or 5 minutes or an hour or 10 hours? So it's hard to know when a reaction is done because it doesn't really look any different when it's done. But we can use TLC to help us monitor how a reaction is moving by counting how many compounds there are. If we start with A and B, at the beginning of the reaction, we're only going to have A and B. But then if we create C, at some time as the reaction progresses and we spot that mixture, it will have another spot that we didn't see before because we just created a new compound. So we can track the progress of a reaction by using TLC and count the number of compounds. Okay, so in 6C, we're going to monitor the reaction. Pre-grind the fluorinone starting material. We're going to change the procedure from the book a little bit and run the reaction for 4 minutes. And we're going to take 5 samples. Small samples of the reaction mixture can be removed while it is in progress. So we're going to get our first sample at 0 minutes, which is before we even add the sodium borohydride. And then 20 seconds later, we'll get another spot. 60 seconds after we start, we'll get another spot, then 120, then 240, and so on. Note that these times are different than what is in the book. We had to extend the reaction time to make sure that we actually finished it. And then we'll analyze by TLC. And so we have to spot a fluorinone standard and a fluorinol standard. So when this new spot appears, we know what it is. So we have to put our reference compounds on the plate so we can compare our unknown to a reference compound. Okay, so here's what we might see when we do experiment 6C. We start with 3 spots. The first 2 spots are our reference compounds, fluorinone and fluorinol, called A and B. Our third spot only has fluorinone in it because we haven't done the reaction yet. We're going to add sodium borohydride, and so after a half hour, let's say, we still see the original spot of starting material, but we see the beginning of a new spot forming, which is our product. After an hour, our beginning spot is decreasing a little bit and our product spot is becoming more prominent. And then after 2 hours, we see that our starting material is gone and we have made a new product. And if we let it go for 3 hours, it looks like we are starting a new reaction and we're making some kind of byproduct. And so it looks like the ideal time to stop this reaction would be after 2 hours. So in all of these parts, you're going to work with a partner. So it will be partners next week, parts A, B, and C. Record in your lab notebook your TLC plate data as you progress through each experiment. So you should draw pictures of your TLC plates in your notebook so you have some evidence of what you've done. A liquid unknown for part A and 3 solids for part B. Plates will be in Ziploc bags, and you get 1 set of plates. So as I had mentioned before, they're kind of expensive, and so before you start marking the real deal, use the practice plates to make sure you're making your spots the correct size. For your pre-lab, don't forget the purpose, methods, and procedures for parts A, B, and C. And since we're actually doing a chemical reaction in part C, you need to draw the reaction in your notebook. There's a pre-lab assignment on Moodle that you need to complete, and there are 3 new reagents for your reagent table: fluorinol, sodium borohydride, and silica gel. Look at the information on the new TLC plate dimension slide in this presentation. It's on the next slide. So in your notebook, on 1 page, make a drawing of the plates that you'll be using in parts 6A, B, and C. This is, if you click on the pre-lab assignment in Moodle, you'll understand what I mean. Hala's intention here is that you use that pre-lab page in Moodle that you're going to turn in. So you're going to fill out your answers on that and you're going to hand it to me. but you're also going to draw those plates in your notebook. So you're gonna have the page, and you're gonna copy that exact page and draw it in your notebook. Be sure to clearly indicate the spacing of each sample. Use a small X to indicate each spot's placement. Make sure your spots are equally spaced. Do not place spots along the edges of the plates. Label each spot with a corresponding compound name or time. You must also make a copy of the plates on the handout. So again, we'll go over all of this at the beginning of lab on Tuesday, the specifics here, but make sure you read through the technique in your book so that you understand before you get to lab, you have some familiarity with what we're going to be doing. The plate dimensions listed in the book, we've changed those as well, and so here are the plate dimensions that we're actually going to be using. So when you need that information, please refer to this page. So you'll place all the waste in the solvent waste bottle in the hood. In part C, you have to quench the remaining sodium borohydride with water and dispose in the label beaker in the hood. So sodium borohydride is very reactive. If we put it in the waste bottle, it could react with something that we're not intending it to react with. So it's important that we make sure that it's done reacting before we put it into the waste. The way that we do that is by adding water. Water will make the sodium borohydride react so that if we put it in the waste, it won't react with anything else. For the lab report, make sure you save all your TLC plates. You can use a scanner or your phone camera to make images for your lab report. Protect your plates by wrapping them in saran wrap and store them in your drawer. Images must be bright, clear, and legible, and all pencil markings must be clearly visible. There's a scanner available in the chemistry computer lab, or it's probably just easiest to use your phone camera. Finally, here's a couple of links that have more information and a demonstration of somebody actually doing a TLC plate, so you can watch it happen before you get to lab. I would recommend looking through these resources. Okay, that's it. If you guys have any questions, please let me know, and I will see you on Tuesday. Bye.